Hello? Başlayabilir miyim Orhan Bey?
Can you hear me now?
Yes, yes.
Thank you.
Professor Kumar. Today we are having a very distinguished guest from University of Minnesota, Twin Cities campus, Minneapolis. Professor Kumar has served as chairman of the computer science department in Minnesota for more than 10 years. And he is currently a Regents Professor at the University of Minnesota. And he also holds the William Norris Endowed Chair in the Department of Computer Science and Engineering. Professor Kumar has authored more than 300 technical research articles and has co-edited and co-authored 10 books, including 2 very popular books titled Introduction to Parallel Computing and Introduction to Data Mining, both of which have been used worldwide and translated into many languages. Professor Kumar's major research focus is on bringing the power of big data and machine learning, which are 2 very popular topics nowadays, to understand the impact of human-induced changes on the Earth and its environment. Professor Kumar has served as the lead principal investigator of a 5-year, $10 million project titled Understanding Climate Change, a Data-Driven Approach, which was funded by National Science Foundation's Expeditions in Computing Problem, with the aim of pushing the boundaries of computer science research. Professor Kumar has served as chairs, co-chairs, and participated in many international conferences in the areas of data mining, big data, and high-performance computing, including the 25th CKDD conference, which is the top conference in the area of knowledge discovery and data mining. Professor Kumar has been awarded prizes by American Association for Advancement of Science, ACM, IEEE, SIAM, and Professor Kumar's research, especially in data mining and high-performance computing, has been honored by ACM CKTD Innovation Award, which is the highest award for technical excellence in this field. I welcome Professor Kumar and thank him very much for his very interesting talk on climate change and how it affects how we can use big data and data science technologies to help solve problems caused by these changes, mostly caused by humans. Our talk will be translated simultaneously to Turkish by our translator. Thank you very much, and please, you may start, Professor Kumar. Yes, your talk.
Thank you, Ahmed. It's a pleasure to be giving this talk on a topic that's of great importance to all of humanity. So with that, let me see if, yes. So as Professor Ahmed mentioned, we are facing a number of environmental grand challenges in this 21st century, and climate change is at the front and center of that. And initially, the expectations were that the changing climate would have a huge impact, perhaps at the turn of the century, like in 2100. But increasingly, we are seeing those impacts much sooner. We can feel them everywhere. And most recent report that just came out a month ago from the IPCC, which is the United Nations panel, it warns of irreversible impacts of global warming. That is, some of the changes may be so severe that we may not be able to revert, even if we take dramatic action. So these are all warning bells coming in from the scientists. We are already feeling them in our experience worldwide. We see increasing frequency of natural disasters of different kinds. Some places are experiencing forest fires, droughts, hurricanes, floods, And no matter where you look at in the world, you see some of these the impacts, or one or more of these impacts. And I believe Turkey is no exception. And of course, everybody's impacted, and the urgency is there. And as scientific community needs to provide information to the policymakers so that they can take the right action. So this is one big challenge that we have facing all of us as a humanity. But changing climate is not the only challenge that we are facing. There are a number of other challenges that are all highly interconnected. And one of them is the fact that our population used to be in the year 2000, just about 22 years ago, about 6 billion. Today, we are closing 8 billion, and of course, increasing. So population has been increasing rapidly. Of course, it's going to saturate, but it's going to saturate probably more like around another after a couple of billion people. Now,
can we have your camera open, Dr. Kumar?
Oops. Oh, okay. I thought my camera was open. Okay. Yeah. Sorry about that. Okay. Yes. Yeah. So, so as the population is increasing, we need to feed the world. And in the past, the increasing demand for food was basically handled by simply converting forested land into agriculture areas, and also by increasing the productivity of the land. And so basically, the trouble is that both of these methods that have worked very well in the last 50 to 60 years actually are now beginning to show strain. As will the old ways of increasing the productivity of land, which was by using more fertilizers, actually is leading to more problems, and I'll talk about that later. And we don't really have many more forests to convert to agriculture. And whatever forests we have, we really need to keep them to be able to save them to be able to sort of keep the greenhouse gas emission in check. A question here. Are you able to see my slides, or you're seeing my face right now?
We are seeing you, Dr. Kumar, yes.
Oh, okay. So, but you should be seeing my slide. My slide doesn't seem to be coming on the screen.
Let me tell the administrator.
Is there any way to handle that?
I will tell.
Information is on the slide. Okay. So basically, there is a tension between being able to feed the growing population of the world, providing people the nutrition, versus the impact it's having on changing climate. Okay. Now, of course, so that's the food security is one major problem. The second major problem, the third major problem is the fact that we also have the supply of fresh water under stress. And it's coming into stress for a number of reasons. Of course, one of them is the population is increasing. The second thing is the changing climate, the global warming, is not reducing the amount of fresh water that falls on the earth, but it's making its supply much more erratic. So you see many more floods and many more droughts. So oftentimes in the same country, in the same state, some parts would be suffering floods and some parts would be suffering droughts, for example, in the United States. Okay? So
Dr. Kumar, your other screen is not sharing, I think, slides. It is,
I see. So let me go back and see if I could handle it. Thank you for warning. And share screen. I think the share screen went away. Yes. And maybe what I would do, yes, okay. And
okay, now it's start to share. Yes.
Is it good now?
Yes. Now we have the full screen. Yes.
Sorry about that.
Yes.
Now, one of the so changing climate is putting big pressure on the water resources. But in addition to changing climate, actually human actions are also putting the water supply at risk. And then there's a big example of that is this freshwater lake called Aral Sea in the former Soviet Union. And you see the picture of this big water body in 1989. And it's a very large water body. And then you see the shape of this water body in just 35 years, and just 25 years later on the right side. So in 2014, it has become a very tiny version of itself. And it was all because of human action. This lake was being fed by two different rivers. and the water from the river was diverted from agriculture. And as a result, you see the lake drying up, the ecology changing, actually the microclimate changing. And this is not just happening in one place, it's happening all over the country. Even in the United States, in Salt Lake, the big Salt Lake for the Salt Lake City actually has shrunk quite a bit for the very similar reasons. So we have a number of challenges here. And then the question is, how do we understand how our stocks and flow of water, fresh water, is changing on the planet so we can manage them better for the growing population and of course for the humanity in general. Okay. The last big challenge I'm going to talk about is the fact that this is not just the availability of water that's under stress, it's actually the quality of water, the drinking water is actually hugely being impacted. And actually a lot of it is being impacted by agriculture. And this is because of the contamination, is because of the fertilizers that are typically used to increase the productivity of the land, to give more food from the same land. They end up getting washed away into the rivers and the lakes and the oceans, and they create these dead zones. And then you can see a satellite picture of Lake Erie, one of the very large lakes in North America. And you can see the huge portion of the lake turning green. And this is harmful algae, which if you drink this water, you can get very sick or die. Okay, so these are all of these challenges that are facing the humanity. They're all interconnected. You cannot solve any one of them without being concerned about the other. So changing climate, food security, water security, and ability to manage energy consumption in a sustainable way. All of these are very highly interconnected problems. They are being studied by a large number of disciplines. And then the question is, what do computer scientists, data scientists what kind of role data scientists have a role to play here? Okay. And of course, the connection through these problems to data science is through data. This is the golden age of data science. Data science has been hugely successful in commercial applications. It has revolutionized many disciplines like computer vision, language translation, and it has changed the way we live, our everyday life, how to interact with each other, how we purchase things, how we entertain ourselves. And then the question is, can the same technology that has changed so much in our daily life, could it also be helpful to address some of these problems? And then, of course, the connection is to the data. And there's a tremendous amount of data about the Earth and its environment that's becoming available, increasingly so over the last many, many decades, especially starting the satellite era about 45, 50 years ago. People started collecting a lot of data. And I'm showing you this animation of the satellite Terra, which has a sensor called MODIS, which takes picture of the Earth every single day, at least once. So wherever you're on the Earth, you look up the sky around 10:30 a.m. and the satellite is up there taking your picture. Right? It's a very coarse picture. It's a very coarse picture, which is a square kilometer is represented only by about 16 pixels at most. But using that data, which is continuous going back to February of 2000, almost 22 years of continuous data, you can create a picture of the Earth every single day as it looked, as well as for every single location, every single pixel on the Earth, how does the pixel look over a period of time? And this data is not just in the visible spectrum, red, green, blue, but it also has multiple other spectral values, which are very informative. So this is just one kind of data that's available. And of course, people all over the world use it for scientific purposes to understand what's happening to the environment. Landsat data actually goes back even to 1972, almost 50 years. Not as good quality, but it's higher resolution and it's every 2 weeks. There are other data sets like Sentinel, which was developed by the Sentinel series of satellites, which are provided by the European Research Commission. And these are much finer resolution data. For example, the entire Earth is represented, the land part of the Earth is represented by about 1 trillion pixels, which is 1,000 billion pixels. So this is a lot of information that's being collected. And in addition to these public satellite data, there are many, many other commercial vendors who provide data at even finer resolution, sometimes sub-meter resolution, and sometimes on a daily scale. So there are basically we are awash in data as far as the Earth and its environment is concerned. Many, many different kinds of data are available. And I gave you a very small picture of it. In addition to these, there are sensors that people have on the earth, in the river systems, waterway systems, agricultural systems that are also creating a lot of data. And the question is, what can we do with all of these data sets and use them? How can we use them effectively to address some of the challenges that I talked about? And it turns out that there's tremendous opportunity to use the machine learning and data science methodologies that people have developed for all of these problems we talked about, like social networking, language translation, and computer vision applications. But so all of these methodologies have a lot of applications for solving these problems. But what I like to also, so that's one message I want to make sure you get out of this talk, that the technology, the machine learning technology has a tremendous role to play here. The second message I'm hoping that you will get is these problems are so complex and so different than the usual day-to-day problem that we address using the traditional machine learning algorithm, that they create new challenges for machine learning algorithms, which means you have to advance them in ways that have not been advanced before. And as a result, you're advancing the frontiers of data science, frontiers of machine learning as well. So that's the pair of theme that would run through my talk. And I'm going to, in the short talk, I'm going to basically motivate both of these themes using three different case studies in a little bit more detail. And at the end of this presentation, I will try to give sort of a more broader view of many other case studies, but much quicker view, where this twin methodology of machine learning trying to help with the environmental problem, but being advanced in the process as well towards the end. So of the three case studies, the first one I'm going to talk about is the need to be able to monitor the forest on a global scale. And why is that important? Because forests, just by being there, by their natural growth, are able to absorb so much carbon that it's equivalent to almost all of the carbon that's emitted by the entire transportation sector worldwide. Every single car, plane, ship, railways. If you look at all of the carbon dioxide emitted by the fossil fuel consumption, almost the same amount of carbon is absorbed by this forest by the natural growth. So, which means the forest can play a tremendous role as we move to a zero carbon future to manage the changing climate. The tragedy is, the irony is that the humanity manages to degrade and burn so many trees, so many forests, that we almost emit the same amount of carbon dioxide in the air just by their degradation. So this is a problem that we are bringing onto ourselves. That means if somehow on a global scale, if we can manage these forests, if we can make sure they stay healthy and they don't burn, and they're kept healthy to store the carbon, there's a possibility that we could actually be they could be playing a major role in the global carbon equation. Okay, and to be able to do that, which means you have to sort of come up with incentives for people to take care of this forest and penalties if they don't. You need to be able to monitor them. You cannot manage anything unless you can monitor. And monitoring of this forest, of course, is a major problem and major interest, except that the many areas of the world are so difficult to monitor because these are the tropical areas in the world where these forest fires, when they burn, they create smokes, and then they make it very, very hard to monitor from the satellite. So how do you build a data science paradigm, a machine learning paradigm that is able to sort of give an accurate picture of what's happening on a global scale, especially in the tropical world, which is the hardest one. There are many, many methodologies people have built for monitoring forest fires, but it's very hard to monitor them in the tropical. So that's one problem I'm going to talk about, and sort of what are the challenges in monitoring of these tropical forests, and what advances have to be made very briefly, and the results that I'm going to show you. The second thing is, many of these forests, of course, when they're burned, they're converted into plantations. Plantation for sugar, for soybean, for oil palm. And they're used. These are of course commodities we use everywhere, right? Everybody uses them in the entire world. But people have realized now around the world that it's not a good idea to convert this forest into large tropical forests into plantations, which is really not healthy for the planet, and especially large swaths of tropical forest in certain part of the world, especially Southeast Asia, are being converted into oil palm plantations. You can see the picture on this middle right column, where you see the right half of the picture is dark green trees, and the left half is these. If you look closely, there are plantations. You see the roads and the little trees in the middle. And it's some of the biggest corporations in the world have promised not to source agricultural products from this recently deforested land. And then the question is, how do you figure out which of these locations have been recently deforested? Because when you look at them from the sky, they look the same. They look green, they look like trees. Okay, so an entirely new kinds of deep neural networks had to be developed to model the space-time behavior of this ecosystem to be able to map this plantation dynamics. And the third one that I'm going to talk about is being able to map the surface water on the earth, fresh water on the earth, how much it is, what is the where it is, and how it's changing at a scale that has never been attempted before or could be possible before. And of course, the example of that is that in February of 2000, about 22 years ago, NASA flew a special mission of the space shuttle, and one of the primary objectives of that mission was to be able to map water on the surface of the earth. So we have a fairly good record of exactly how the water bodies look like, let's say on one day or 1 month in February. But we are trying to figure out exactly how it's changing over a period of time, and how the human actions and changing climates are impacting it. So all of these are very interesting questions. And again, I'm going to talk about some challenges in monitoring the dynamics of surface water and why, and what we're able to do using machine learning algorithms. So these are the 3 case studies. And again, each one of them, as I said, I'm going to briefly talk about the challenges and the results of the methodology that we're able to produce global scale results. Okay. So the first one is about the ability to map forest fires on a global scale, but especially in the tropical forest. And on the face of it, this problem actually looks fairly standard in the sense that this is something that you could potentially solve after your machine learning, data science, data mining 101 class, the very first class you take. You sort of say, well, give me the training data. You have the satellite data, you know what locations are the forests that have not burned, and what are the locations of the forests that have just recently burned. And if I have the multispectral attributes, features from these locations, I can feed them into a machine learning algorithm, which can use the data to train itself, and I should be able to look at new pixels and figure out whether they're burnt or not. So it seems like a very simple formulation. The only problem is that there's a huge amount of spatial and temporal heterogeneity when you look at this relationship between the spectral signatures that are seen from the satellite and whether that pixel happens to be burnt or not burnt. Now, this notion of temporal heterogeneity in both space and time runs through almost all of the environmental problems, because the entire Earth environmental structure is very, very complex. It changes from one place to the other, and it changes over time. So this is one big problem. So we have a lot of data, labeled data for forest fires in North America. For example, the state of California, which has a lot of forests, which burn a lot, and I'm sure you read newspaper stories about big forest fires in California. So the state of California maintains a very good record of locations that have burned. Each year they will issue a set of polygons which sort of inform people, the environmental community, as the areas that have burned in the previous year. So we have plenty of labels potentially, except that if you build a model using those labels, it won't even work very well in other parts of the US, let alone the tropical one. And certainly the methodologies that people have built for monitoring the forest fires on a global scale, they tend to grossly underestimate the locations or the amount of forest that is burned in the tropical area. So that's one big problem. That is, and then of course in the tropical world, there are no labels, because when the fires burn, the skies get very dark, and the fires burn for months, and it's very hard to see what's happening there. The second problem is, and this applies to, again, many of the environmental problems, that the target class here is highly imbalanced. So which means in a typical year, in a typical time, most of the locations are not going to be, most of the forested areas are not going to be burned, only some parts burn. And which means if your machine learning algorithm has even small amount of false positive rate, it would end up making a lot of false alarms, and then it'll give you very inaccurate picture. And that's, of course, that's a problem that's faced in many cases, many problems, not just environmental problems. Okay. And the third thing is, if you are trying to build a model, and if you're trying to figure out whether the model is good or not, in areas where you don't really have proper labels, how do you even evaluate what you're doing is good? So basically, the question is, when you are in the dark, when you have such challenging environment, how do you even build a methodology that you can work in the challenges, and whether the methodology is actually good enough or not? So there are all of these challenges that sort of that come to bear, which is very which make the problem very difficult to handle. So all of these problems were handled using this paradigm called rare class prediction in absence of true labels. But when highly imperfect labels are available for all instances, that means you have from satellite, you have some information about each of these, which gives you very inaccurate picture of whether the location is burnt or not. But then, and you have it for every single pixel every single day. The question is, could you convert? Can you build a methodology that gets you a very high quality labels, and then give you some trust in them? So this is a long series of work that we did over a period of years. I'm not going to go into the methods details here, but once this methodology was developed, it was able to be applicable on a global scale, and especially in the tropical world, it was able to find far more accurate picture and far more complete picture of what has been burned on a global scale. Just giving this example, that in this broad swath of tropical forest, you can see that the state-of-the-art product from NASA had about 160,000 square kilometers of forest that was burned. And it turned out that this methodology RAP that we developed has almost 3 times as much it was burned. And just to give you a sense of how accurate and comprehensive our product is, I'm showing you a picture of a portion in South America from the Amazon forest. And the 3 panels here, the leftmost panel shows you a picture from year 2000. And if you look at this picture, it's mostly dark green. It has some very white patches, which are clouds on the left side. On the right side, you can see some white patches, which are really roads and deforested areas. So you can see that dark greens are all forest, and the white patches on the right side near the roads are all deforested land. So this is what the image is seen in 2002. Now, if you look at the same location, same area in 2015, about 13 years later, this image has no cloud whatsoever. So every patch every white area that you're seeing is actually a deforested land. And you can see that you see many more white scratches all over the place. And remember, this is an area which is about a couple of 100 kilometers by a couple of 100 kilometers. It's a very large area. And on the third panel, we are plotting every single location that was detected as a burned location by our algorithm called REP. So all the yellow and the red points, all of them are the locations that are detected by our algorithm, and they match perfectly this deforested area on the middle. You can, if you watch this screen for a few minutes, you'll be able to see that every single patch on the left side has been picked up on the right side. This tells you how comprehensive it is, or how complete it is. And then I changed these pixels to 2 different colors, yellow and red, because the red pixels are the only one, about a third, almost a third in this case, which are also found by the NASA's state-of-the-art product. So you can sort of see this confirms the fact that technologies that were developed before us were very incomplete, and were able to only find a very small picture of what has been done. So this is sort of a demonstration of the fact that the machine learning technology can stand up to the challenge, can be advanced, and as a result, solve a problem that is of a great interest on a societal level. The second problem I'm going to mention, again, rather quickly, is, as I mentioned to you, a lot of these plantations, a lot of these forest areas are converted into plantation. And then on the previous picture, you saw the plantation, they're mostly soybean and sugarcane plantation. But in the Southeast Asia, these forests are being converted into oil palm plantation. Now, this conversion of forests into oil palm plantation started with a good intention, because initially the hope was that oil palm can serve as a fossil fuel, which is renewable, which means we're not relying upon the traditional fossil fuels, which sort of can never be regenerated. Here is oil palm, you can regrow these trees. So it turned out that people figured out, and the environmental community very quickly figured out, that actually this conversion of forest to oil palm plantation is so bad for the environment, even for the greenhouse gas emission, that it's going to take centuries of time before we can recover the lost carbon that's in the soil of this forest and this tree. So this is it basically turned out to be a good practice. It was considered to be a good practice to begin with, and it turned out to be a major disaster. So everybody's trying to reduce this practice. Everybody's trying to discourage this practice, which is why many corporations are saying we're not going to be burning rainforest for palm oil, which means you want to discourage any product that's coming out of this area. And as a result, many corporations, many nonprofit entities, many nonprofit organizations have started building maps of what locations got converted from forested tropical forest to oil palm plantation in recent times. So there is this map on the top middle that you can see here. It's called TP 2014. It's a map that's created by Transparent World. It's a nonprofit organization. And all of the pixels, they're sort of hoping, they're sort of claiming that these are the oil palm plantation. This map is useful, but the only thing is that it's highly inaccurate. Almost more than half of these locations that you're seeing here, right, actually are not plantations at all. Okay. Then there's another organization that came up. It's called RSP, Roundtable on Sustainable Farm, and they created one map for 2001, one for 2005, one for 2009, and more recently they have released one for 2014. And these maps are far more accurate, but they are much less complete in the sense that they're missing quite a bit of oil palm, even though whatever location they say is oil palm is actually a conversion to oil palm. The trouble with all of these approaches is they are manual in the sense that, of course, they use a little bit of standard machine learning approaches, but they're primarily manual. People are poring over these satellite data sets to figure out whether it looks like an oil palm or not. It's a very difficult way of solving this problem. It's incomplete. Data products are incomplete. So the question is, how do you build an automated method that could work with these incomplete data sets as training sources and take into account this process of the fact that this oil palm trees sort of go through a process of trees being deforested, and then this plant, the trees are growing slowly, maturing into oil palms. If you can sort of somehow leverage that into machine learning framework, then there's a better hope for building a more accurate map of what's happening to the tropical forest and the conversion to the oil palm plantation. So this methodology had to be developed, and how do you learn? Challenges turn out to be, how do you learn from multiple annotators that are imperfect? How do you handle temporal heterogeneity? Again, that runs through everything that you do in environmental sciences, and how you incorporate process-based information. And as a result, we were able to build this methodology that sort of gives you this continuous yearly view of what's happening in this Southeast Asia area. We have tropical forests typically converted into oil palm plantation. So all of the red locations are known to people as oil palm plantation as of 2001. And if you see this animation, and if you watch this time, 11, 2012, 2013, 2014, and then go back to 2001, and you can sort of see how these areas have grown. You can sort of understand exactly what years the conversion was much more drastic, how is it slowing, and so forth. And there's a lot of international pressure, which is, of course, slowing this practice. So basically, this allows people to manage, and as a result, monitor and then manage this very tremendously important ecological resource. Now, the fact that we can figure out what areas have been converted recently from tropical forest to oil palm plantation, and the previous work also allows us to figure out whether these plantations were put in place correctly. Because if you in Indonesia, for example, if you go to the government and ask for a permit to create these oil palm plantations, the government expects you to cut those trees, move them away, and then put the plantation. But oftentimes people would simply burn those trees because it's very hard to there's no infrastructure in this tropical forested area. So the question is, when you burn these trees, how do you know that you're only burning the amount that you need for your plantations? You could be creating large forest fires that are spreading all over. Okay? And you can actually check that using our case study number 1. So this is a part of West Kalimantan. This is a part of Indonesia. If you look at all of the green pixels on the screen, these are all plantations that were converted between 2001 and 2014. Now we can tell which of these locations were burned. And it turns out that about almost half of these locations actually have a burn scar, which means people did not really build them properly. They really burnt the trees. But when you burn some forested area, the question is, you put a plantation in a small area, but what else got burned in the process? What is the collateral damage? And using the case study one, we can find that as well. So blue pixels are all collateral damage. So basically, you were trying to put a plantation in a small area, but the fire that got started actually went ahead and burned much, much more. So it's almost like a tremendous, you can sort of actually figure out not only whether you did your right thing, but how much damage you caused to the rest of the ecosystem just by using this approach. So again, this sort of shows you the power of machine learning and data science methodology, and how do you provide some critical information for the management of these resources. Now, my last case study, in which I'll go into more detail, is being able to map the surface water, stocks and flow, mostly talking about dynamics of surface water on a global scale. And as I mentioned to you, this is such an interesting problem, such an important problem. And there are many, many aspects of this, and I'm just going to cover a very small aspect in the short talk. NASA flew a mission of the space shuttle to map surface water on one day, which means we have a lot of labels from just one day or one month of February 2002 to 2000. But even then, this problem is very hard because of the heterogeneity in space and time. And again, as I said, this thing comes up again and again. And then you can sort of see that if you look at these water bodies from this Earth through a false spectral composite, you can see that lakes, even in nearby locations in North Africa, look very different from each other, in the spectral space. And in the lower part of the left column, you see the same lake in Argentina at two different times, and it looks very different, even though it's the same lake. And again, to heterogeneity over time versus space. And on the right panel, you're seeing an animation of data from a lake, from Poyang Lake in China, which is actually not too far from Beijing. It supplies fresh water to Beijing. And whenever you see this dark orange color, the data is missing. So a lot of data is missing just because of the quality issues. And when the data is missing, of course, you have no information. But imagine, because this data is being seen from the space, even if you think when you have the data, actually it could be wrong data. Which means if you build a really good machine learning algorithm to classify pixels on the Earth as lake, water, or land, but if your data is garbage, then the output would be garbage. So all of these issues sort of come to play and make this problem very, very hard to produce global scale understanding of how the surface water is changing, even using ample amount of data. So the machine learning contribution happened to be here as to how do you incorporate other information like physical laws and other process level information in the machine learning framework. And again, these are a methodology got developed as a result, and we have now a global product, actually multiple global products that give you a sense of the surface water and how it's changing over the on the Earth during the satellite era, especially the Moody's era and the Landsat era. So the first viewer, of course, anybody can go to this link, type it, and see this viewer for themselves. This one maps the surface water of all the dynamics of all the surface water bodies on the Earth that are more than 2.5 square kilometers. So this is a coarse model in which if your body is large enough, if it has at least 10 Moody's pixels in it, it will be mapped in this viewer. And these maps are, of course, available every 8 days, just to handle the water quality issues. There's another product that we have that I'm going to talk about very briefly, which provides you the monthly time series of change at 30-meter resolution available using, it's a product called RealSat. So basically, both of these products are available in public domain for the scientific community to use. And they allow us to understand a whole bunch of things on a global scale. We can do local to regional change analysis. We can figure out the glaciers that have been melting in some very sensitive part of the world. We can see the changing river morphologies. We can identify construction of reservoirs. We can find surface relationship between surface water and the groundwater. All sorts of studies can be done, and I'll briefly mention only some of them here. So if you go to the viewer, you will see little dots which sort of tell you where these water bodies are. One of these dots happened to be Don Martin Dam in Mexico. The viewer also shows you for this dam how many Moody's pixels that this dam have over a period of time, going back to 2000 when the Moody's data was available. And remember, 4 pixels make a square kilometer. So if you have 800 pixels in a water body, then you have about 200 square kilometer size is the water body. It's a pretty large water body. And you can see this water body has been changing quite a bit over the period of last almost 20 years. You can also, the viewer will also let you see this modification, will also see the size of this water body as it's changing on a yearly scale using the Google time lapse. You can take these water bodies because you have this time series of how big they are. You can color them, whether they're increasing, which is red in this picture, or decreasing, which is blue in this picture. And you can see in the South America, a lot of places you see a lot of red dots, a lot of places you see green dots, and then especially in Argentina in the south, you can see that huge blob which is all green. Let's zoom into it. It's actually completely green everywhere, almost everywhere. And if you zoom in here, you will find it's mostly an agricultural area. And if you compute the total amount of area in this green dot, it's about 12,000 pixels, which is about 3,000 square kilometer of surface water that has almost shrunk over the last 20 years. And you can actually see its growing and shrinking behavior actually from Google Time Lapse. So what I'm saying that you have your surface water of the earth on your fingertips. Okay, you can go to other part of the world and you see some places in the world, like in the Tibet, in the Himalayan glaciers, you see a lot of red dots. And of course, people have known that because of the global warming, the glaciers in Tibet are sort of shrinking because they're melting because of the increasing temperature. And the water, of course, flows into the river, but also gets trapped into these lakes, and the lakes become bigger. And people in the past have been studying these areas using snapshots of Landsat data and having a picture for a certain area in 1 year or another year. But this viewer sort of gives you a very complete picture on a sort of a global scale. In the viewer, you can sort of go in and you can find out, this is for each of these lakes, what areas have grown. You can see the dark black areas, which are the water as of 2000, and the red areas that have increased. And same thing on another area, and then you can sort of keep going, and you can go to any of these areas and see Google time-lapse images that confirm that the viewer is actually showing you the right thing. And for this entire area, you can actually find out that 40,000 square kilometer of new surface water has shown up in the Himalayas in this area, which is about 10,000 square kilometer of water. And these glaciers are really important because as if they melt away, they literally supply water to rivers that feed about 2 billion people on the earth: India, China, Southeast Asia. So this is a very critical area for the humanity. And you can study this. You can sort of figure out how the surface water was changing, how the water quantity may be changing. And once you monitor, you have a chance of being able to manage them. You can see if the river meanderings all over the globe, because the river meanders, and some place will lose water and some place will gain water. As a result, you'll have red and green dots right next to each other. So the river meandering is a environmental phenomenon that people would typically study one river at a time. And here, this product allows you to study them on a global scale very easily from this viewer. You can see the island shrinking as the sea level is increasing. Some of these islands are shrinking, and as a result, on the land, you will see some surface water bodies showing up, and you can catch them using this methodology. And I promised you that we also have another product which actually looks at very small water bodies as well, water bodies that are as little as 0.1 square kilometer. And this product, RealSat, has 700,000 water bodies below 50 degrees north, where much of the humanity lives, and it has about, and it's actually a picture of water bodies which is about 3 times as more comprehensive as the most complete data set available to the ecological community, which is only about 250,000 water bodies in it. And not only that we have so many water bodies, but we also tell you how they're changing from day to day. I mean, from month to month. So this technology is very comprehensive. And so you can identify new lakes and reservoirs, you can find out the changes in the water bodies, and the data like this could actually help calibration of flood models, provide advanced warning for the floods and the droughts and so forth. And just to show you how much more complete this data set is, this picture actually shows you dots, the dots red and green, and all of these dots are sort of actually water bodies. And the red dots are the ones that are known to the ecological community in the standard data set. And you can see almost 2/3 of this image has blue water bodies. And if you zoom in, you can see these water bodies actually happen to be quite large, and yet they were missing from the existing data sets. So this is the power. And now you can sort of study on a global scale as to what's happening to these water bodies, because you can figure out collectively, are these water bodies losing surface area, or they're growing? And you can see in the last decade or so, there's a lot of stress on the water body that people are experiencing all over the world in different continents. Okay, so with that, I'm sort of coming almost to the end of my talk. So in this last panel, what I'm trying to tell you is that I showed you 3 different major case studies where machine learning have been able to advance and produce global scale products. And remember, all of these products that you saw on the previous slide were produced by students in computer science. They're all PhD graduate students in computer science, working in one place, literally sitting in one building, using the data from these global satellites, building new algorithms, and then producing data set that can be used in the entire world by the scientific community. Okay, so those were the 3 examples. And on this slide, what I'm trying to show you is other ways machine learning has been used in our group for addressing a bunch of other environmental problems. And on the screen, what you're seeing here is 6 different examples. On the top left corner, what you're seeing here is a data set that we created for monitoring the ocean eddies. So ocean eddies are these little whirlings of the water. So basically, water is sort of moving around one place to the other. These are very large eddies. They actually have size of oftentimes hundreds of kilometers, in this hundreds of square kilometers. They're very, very large water bodies. They may move from one place to the other. They're the primary mode for the ocean, the ecology, to sort of move energy and plankton and the food from one place to the other. And that they play a very, very important role. Gulf Stream, for example, is sort of moving a lot of these eddies as well. So basically, there is a tremendous amount of motion in the ocean, and people need to understand exactly how these eddies and their motions are changing. And it was very difficult. It was very difficult to analyze, study these ocean eddies, because one easy way is to put some sensors in the ocean, like buoys. And if the buoys move around from one place to the other, then the ocean eddy is in that place and it's taking from one place to the other. But that's a very difficult way of collecting data. Now, in one of the PhD students in the group, working with a few other students in the lab, created this global data set of ocean eddies over a period of 20 years that is now being used by the entire oceanography community. And again, it will involve entirely new kinds of spatio-temporal pattern mining algorithms that were sort of able to track these objects, ocean eddies, identify them, and track them over a period of time. The middle top row is showing you a different kind of data set in which you are looking at the data coming out of the climate models and sensors. It's called reanalysis data, and then trying to figure out teleconnections between the relationship between one part of the globe and the other part of the globe. That is, how does the climate in one part of the globe impact the other part of the globe? For example, many of you may have heard of the climate phenomenon called ENSO, the Earth, it's called the El Nino phenomena, where the ocean warms up in the Pacific and it sort of causes either warms up or cools in the Pacific, and it causes changes in the climate pattern all over the world. So this is just one example of a climate teleconnection. And the question is, can you find such a relationship automatically using machine learning algorithm? And again, using a methodology that are not too different than the ones that people use for social network analysis. A series of students and PhD dissertations, they basically created this methodology in which you could find entirely new patterns in the climate system. And many of the same methodology actually then was used on the brain imaging data, in the sense that the algorithm is the same. You take the data from the climate sensors and you produce the climate teleconnections, and you apply it to the brain sensor data, fMRI data, and then it produces relationship between different parts of the brain. The third top panel is talking about a problem that goes back to one of the challenges I mentioned to you on the earlier slide, which is as we are trying to manage the food supply for the growing population, of course, we are trying to make sure that we don't deforest the world and destroy the planet, but we also need to make sure that the world's food supply become more productive, agricultural land becomes more productive. And as a result, you need to figure out the methodologies to increase the yield of this land. And then one of the major input that goes into is to be able to figure out what locations people are growing what crops. And that's a very difficult data set to have. That is to have a data set in which you can tell what locations in the globe are growing. Is it growing wheat or crop? Is it corn or sugarcane or something else? And there's a data set that's produced in the United States by the US Department of Agriculture, which every year it produces a data set at 30-meter resolution and giving all of the crops that are grown in the United States. And in this picture, you see two pair of pictures. You can see the left picture, which is produced by the USDA, and this is one of the best data sets you have on a large-scale data set you have for crop mapping, and yet it turns out to be highly incorrect, and for many crop classes, especially not the major ones, and you can sort of see, it's very spotty. Now, this methodology that the students developed very recently is to take this USDA data set as a training set and build an entire methodology that gives you a much higher quality crop labels at much greater spatial resolution, which is you're seeing on the right side. And of course, the methodology required ways of evaluating what you're doing is correct. It's a very complex methodology, but it is able to result in much better quality results. On the lower part of this panel, you're seeing three different environmental problems being discussed. At the lower left is the one in which you're trying to figure out the water, health of the water in the lakes, in the freshwater lakes, and the temperature is one component of this. The second one is in the bottom one is looking at the hydrological modeling, which is used often to figure out what areas are going to be flooded or drought or have drought in different situations. And the bottom right most is the problem in which you're trying to figure out the greenhouse emission coming out of the agriculture. Agriculture is responsible for almost 20% of the total greenhouse gas emission. And if we do it right, people believe that we could make agriculture a sink of the greenhouse gases. So exactly how do you figure out, how do you do the proper modeling of this greenhouse gas emitted from this agricultural area? So they're all three very important environmental problems. All of these three problems are solved typically using physics-based models that the scientists in these communities have developed over a period of decades and decades. It turns out that those models are sort of not as good as they like them to be. And increasingly, people are beginning to study machine learning as a solution, but machine learning doesn't work very well because you need a lot of data. And there's a new methodology that we have developed, which was inspired by the three case study that I presented to you, in which we are trying to bring machine learning together with physical modeling to make both of them better. And then this area has seen tremendous advance as a result. So my goal is to sort of tell you that there are many different ways machine learning can come to help these environmental problems. And many of these new problems actually challenge machine learning paradigm. So you can't just simply take existing algorithms and then use them to solve this problem satisfactorily. You have to make advances. So it's in some sense gives computer scientists, data scientists, something to work on their research, and then of course the environmental scientists solutions to their problems. This research, of course, is funded by a number of different projects. One of them is the NSO Expedition project, and which was a project between 5 different institutions and a close collaboration between physical scientists and computer scientists. And this is just a highlight of some of the reports and the papers that sort of came out of this. And let me just conclude by sort of saying that the big data and machine learning offer tremendous opportunity to increase our understanding of the Earth's climate and environment, and addressing challenges that are unique to these problems actually require major advances in machine learning. And these novel approaches that sort of we found very useful are the ones that somehow try to infuse the scientific knowledge into machine learning, and we call this a theory-guided data science paradigm. and they have are increasingly being these methodologies are being applied to many diverse domains. With that, let me just thank my team members. You see pictures of about 24 graduate students who have graduated from my lab in the last 10, 12 years. All of them, nearly all of them had a PhD, and they're all employed. Of course, some of them are in the academia, working on an environmental problem. Many of them are, of course, working in companies like Google and Microsoft and Facebook and such. And this work has been funded by lots of different grants, NSF, NASA, and USGS, and many other agencies. And we have many collaborators across the world, but certainly across the US and with different universities. I'd like to acknowledge them all, without which this work won't be possible. Thank you, and I'm going to stop here and see if there are any questions.
Thank you very much, Professor Kumar. In fact, one question that comes to me is, since you have worked so extensively on big data and machine learning, and you are working for really big and important research projects, how do you see the future of computer science with big data and data science?
The future of computer science, and especially data science, is really bright, because if you look at the history of the field, going back to almost 60 or 70 years, computers, we have been very good in building computers. We successfully build a faster and faster computer. Every decade, the computing power went up by at least a factor of 10. We made this computer more powerful, and we gave them to other communities to use them. So for bulk of our existence as a field of computer science, we provided more and more powerful tools to the other scientific communities. Now, what is becoming clear over the last couple of decades, but certainly over the last decade, is that every single discipline now sees critical need for strong, tight integration between their field and data science, okay? In the sense that they feel that they cannot advance further unless they have a very strong connection to data science. So you would see now data science initiatives being launched in the universities worldwide. You will see data science programs being launched, everywhere, and in all of these initiatives and programs, you see very strong participation of computer scientists, which are traditionally, the data scientists, but also the material scientists, the chemist, the physicist, the earth scientists, and so forth. Right. So this is a phenomena that's happening. It's actually and it's only going to grow further with this new paradigm in which we are bringing scientific knowledge and machine learning together. And just to give you an example, USGS, which is one of the very strong collaborators in our work, basically their mission is the USGS water mission basically has this scientific knowledge guided machine learning as part of their blueprint now. This is the methodology that they're going to be using as we go forward. Using that methodology, because their charter is to be able to manage and monitor these lakes. They have 186,000 lakes in the US that they try to manage. They only have sensor data for only about 8,000 of them, like about 10,000 of them. And using our methodology, they were able to create surface water temperature record of all of these 186,000 lakes. And this was like, this piece of work was just finished in the last few months, and all done by a PhD in computer science. So you can see the power of PhD in computer science, people who are sort of sitting in a room working with a computer, and then being able to provide information on a global scale that people could not imagine. So this tells you as to how much role computer scientists, data scientists have to play in addressing many challenges that are facing other disciplines.
Thank you very much. Also, I think you have given a very good example with this palm oil production, that actually people claim some good, intentions, but eventually it turned out to be quite harmful. So,
Yes.
do you think we could somehow get help from computer science and data science so that will we ever be able to prevent humans, making such wrong decisions using such?
Yes, that's right. Again, and again, this has happened not just for oil palm. It has also happened for ethanol. Basically people growing corn to be able to convert it into ethanol as replacement for petroleum. And as a result, as people started planting more corn in the United States, the land for soybean became smaller, and then as a result, in Amazon, huge soybean plantations got planted. Because the world is connected. If you change one thing in one place, it has impact everywhere else, right? So basically, all of these things are interconnected, and I think the impact. The key thing is to be able to understand the impact of these different interconnected components on each other. And the tools that people have had so far in the scientific community are these models that create models for each of these components one at a time. And because each of these models are imperfect, when these models connect with each other, these errors propagate across. And what this machine learning methodology, which especially we call knowledge-guided machine learning methodology, is it has a potential to circumvent some of these issues and provide better information. So computer scientists cannot keep people from making wrong decisions, but they can hopefully tell them the consequences of those bad decisions, and hopefully they will use that information to set themselves right.
I think you have achieved great results with this research work. Is this 10-year project completed now? 5 years?
Yeah, that project is completed, but this project is sort of continued by many other grants. There are those projects, of course, have term limit, but the current projects are funded by the USGS, and National Science Foundation is funding it through 4 other projects right now. One of them is a $25 million project on understanding, on advancing the climate science through machine learning. It's again involves a lot of universities. It's anchored at Columbia University, and the University of Minnesota is a part of that collaboration. There are many other projects we have at the University of Minnesota on collaboration between data scientists and hydrologists, data scientists and freshwater ecologists, agricultural scientists. So there are many such projects that are continuing. But the expedition project played a very important role in creating an ecosystem in which we could build a technology that can be built upon further by us and by other people as well.
And you also have a very nice software engineering program in University of Minnesota.
That is true.
Yes. How about recently there are also new departments coming up with cybersecurity and game engineering. So how do you see the future directions in those areas?
So all of these areas, okay. So when I said data science and machine learning is connected to all other disciplines, but machine learning is also connecting to every single sub area within computer science. If you go to software engineering community, they are using machine learning to find errors in their software codes. So for example, right? So machine learning is being used in computer architecture design and in software engineering, and you pick up any field of computer science and you will see machine learning being used there. So it's the new age, which means it's the perfect time to be a data scientist. And the world is sort of just open. Opportunities are open in front of us. So it's a very exciting time from that perspective.
I hope you will serve University of Minnesota for many years to come, and you really look very good, and I'm happy to see that you are achieving so much, and your work is being appreciated by in United States and worldwide. And I hope your contributions will continue to come, Professor Kumar. Thank you very much for joining this seminar and helping these young scientists and students in Turkey to appreciate computer science and machine learning and data science. Very, very hot topics. Thank you very much.
Thank you very much.
Have a nice time and see you.
Yes. Bye-bye.
Bye-bye.